So, Bill Veenhuis, I'm a solutions architect out of the Detroit area here. So I support the automotives, but historically at NVIDIA, 8 years ago, I was the solutions architect for Michigan, Ohio, and Indiana. So we've done a lot of growing, a lot of customer base and change and stuff like that. So what I'm here to do today is talk about some of the NVIDIA technologies, especially related to data analytics. The interesting thing is a lot of people, when they hear about NVIDIA, first thing they do is think graphics, and they think graphics hardware and gaming. We support an entirely different industry, right? High performance computing, high performance data analytics, right? Machine learning, AI processing, recommender systems, things like that. We're in a whole bunch of walks of life, but more of NVIDIA is actually on the software side than the hardware side. I mean, let's face it, we take advantage of the hardware changes and the innovations and stuff like that. But at NVIDIA, probably 7 out of 8 things we invest in is software. And the majority of that software actually isn't monetized. It's given to the community for free. So these are sort of the areas I'm going to touch on. If you don't know what NVIDIA is, a GPU. Rapids are our database acceleration engine, open sourced. CuPy, you're going to see some code here. It's not all about flashy slides here. And I'm going to talk a little about MERLIN in the end. So GPUs, right? This is the ubiquitous slide, right? From an NVIDIA perspective, right? There's certain content of any code that can be parallelized, right? And you can take advantage of using a parallel accelerator like a graphics processing unit that NVIDIA has to offer. And I actually came out of Silicon Graphics early on in the early 90s. And we invented IrisGL and then later on OpenGL. And so we know all about the whole graphics language. And so that's sort of my long-term heritage there. And we did that very well. And eventually, when we started designing these GPUs, these graphics processing units, we realized a tremendous value in terms of high performance computing. So about mid-2000, we sort of did a directional change. We decided just not to make a graphics card, but we made a compute card that did graphics better than everyone else. So one of the things here is you can take your code and you can run parts of it on the GPU and parts of it on traditional CPU technology. The interesting thing, though, is that's really not what NVIDIA is about. What we're really about is things like this, multiple levels of innovation inside our graphics card. Everything from being able to fit the problem, right? Sizing up the memory accordingly, right? The other thing is adding accelerators. Things like video encoders or decoders, right? Can we save you a few steps along the way in that pipeline, right? Maybe I need to change the color space. Maybe I need to change the brightness. So we have those encoders and decoders that are actually built into the chip technology that saves you a crawl, right? Basically, some of our streaming engines, like GL Streamer supports it. We also have tensor cores, and tensor cores are used for AI innovation. But more recently, we're starting to actually see CAE applications. Honestly, in the last couple of years, bioinformatics has been an area that the tensor cores have been heavily utilized, obviously for COVID research. We actually have one of the 4th largest computer systems in the world that we sort of built and donated for COVID, and just had an open door policy. If you had a problem that you could find a solution to this monster we're all dealing with, come on board. And for folks like Jared over here and me, we actually had to fight for an opportunity to get on the 4th largest supercomputer in the world. Right? We gave it to everybody. The other thing is interconnect, right? Is be able to talk to multiple things at the same time, right? And multiple GPUs. And what I mean by that is because that first slide kind of showed is we were segregated. This GPU on one side and the CPU on the other. You have to be able to communicate, and do I want to have to use a CPU to communicate to my neighbor's GPU all the time, right? And so really what NVIDIA is about is all that innovation that goes into the GPU. It's not about fancy graphics, and this is one of our revisions. We don't have the RTX ray tracing capability in, but it's not about graphics, it's about the whole ecosystem of opportunity there. Anyone ever heard about Rapids from NVIDIA? Okay, we got one person. I know Jared has. Couple people, okay. So a couple years ago, we started with looking at the opportunity how to accelerate database transactions. And we got a couple folks that actually wrote our linear algebra libraries and stuff like that, kind of gave them the task, and they sort of developed a capability here. So Rapids, really, what we just did was we took sort of what was open industry canvassing, right? Figure out what people were using, right? I mean, I'm an engineer by training, not a scientist, not a visionary. My task is to make things better, more efficiently for the betterment of humankind, right? I love science, but it's how I use the science is important, right? And so one of the things that we did, that philosophy sort of stuck through, right, is figure out what everyone's using. And then if we can figure out what they're using, figure out why they're using it, and how we can complement it. The idea of NVIDIA wasn't to change the way you functionally did anything. It was to take what you're exactly doing and make you better. And sort of this was that philosophy, right? So this uses kind of an AI training type thing. We were doing some training preparation, sending it over to some machine learning or AI or deep learning algorithm, and running it through a given number of paces to determine hopefully it's not a frog or a dog or an elephant, but and then we're doing some visualization, right? See how accurate you are. An example of that today is if you're at Home Depot. Home Depot has those little checkout scanners. You scan the object. If you flip it over, you might notice there's a camera there. And that camera does two things. One of it identifies, am I scanning a 2x4? The other one in the future, you'll see that it could actually figure out, oh, there's no UPC code. What is it for me? I don't have to go put the red light on and scream and yell, there's no UPC code, right? It's actually ability to self-identify the object and determine the price, right? So those type of scenarios are going on. But this is where we kind of started. What were people doing first? And what we did there with Rapids is we basically said, okay, I want to take all your elements and have an equal equivalence, right? And that's what we did. We went out and said, okay, we want to have equivalence and we also want to have the best class acceleration with it. Sometimes the problems are 10% accelerated, sometimes they're 150x accelerated, right? But the idea there is to allow you to make a change seamlessly without an uplift charge, right? A tremendous uplift charge. So things we've done here is, you might have noticed, instead of using the traditional CPU memory, we move it to our graphics processing unit. One of the things is graphics processors have tremendous floating point performance. But I don't care how fast your clock is, how fast your frequency is, if I don't give you data to do anything useful with that clock, it's irrelevant, right? So one of the things we do is put a lot of high performance memory right into the graphics processor unit to be able to facilitate keeping the funnel full, right? And so that sort of was this philosophy here, right? Is take all these libraries, do the math you want to do today and are doing today, and take the bottom end of it and make sure the hardware accelerates it to the maximum. So I told you I was going to show you some code, right? And this is really the philosophy here, right? It's taking what you've done and making it better with a lower cost of uplift, right? And sort of, you'll see some of these slides here, right? First one's Pandas, right? I mean, the simple Pandas, reading in some data, right? We have a real easy equivalency, right? I mean, I grew up in Linux and Unix and whatever, and actually Cray-Days in the late 80s using VI, right? I mean, I could literally bulk switch this stuff, right? Bind switch, boom, done, right? I mean, that's how easy it is if you just understand the relative cost, right? I wouldn't say do it on a million lines of code willy-nilly, but it just gives you an idea, right? We pretty much either from Pandas, Spark, NumPy, I think I have scikit-learn here, and even Matplot, right? The visualization. We sort of have an equivalency, right? And in this one I put networking, right? CuGraph, right? So the idea here is to allow you the opportunity to see if GPUs can innovate your process and accelerate time to solution, time to discovery, or improve your overall application performance. This slide needs a little bit of conversation on. The yellow is the compute piece. If you notice on every one of those slides, the compute size is about the same, right? So it doesn't matter. You can't fake not doing the math, right? I mean, that's the problem, right? Is that you're still going to spend, like in this case, 2,000 rough seconds solving your problem, right? The other things are things like, how do I load my data, right? Rapids has this concept of an open source CUDA frame. It's CUDF. And the nice thing about CUDF, it's kind of a neutral format that fits well in a GPU. In other words, it's free and easy access. Every time I get a piece of data, I get all the value out of that page versus 2% or 2 bits out of the page. So we align everything for that ebb and flow very efficiently. So the purple is sort of the load and store, ETL kind of thing, right? You'll start seeing here, and we didn't cheat here, all these other ones up on top are CPU nodes using multiple nodes. We actually use 2 nodes in this case. But you'll see the instant acceleration, right? But like XGBoost, that's your computational phase. Guess what we do very well? Parallel processing, right? So you see our time goes to nothing, right? But the reason this slide I included here was there's other elements here that you can't control effectively if you don't have data well formed, right? I mean, like Pandas, Python strings and stuff like that, they're not very efficient, right? They reach around code and memory, grab everything they need to assemble your problem, right? We basically, with Rapids, take that same data, allow you to painlessly ingest it, and reformat it very efficiently to leverage the GPUs. The other thing here is we've done a bunch of improvements. More recently, we got a whole bunch of Pandas innovations, right? I mean, we used to go after the numpy people and scikit-learn and all that. That was kind of easy, low-hanging. But nowadays, I mean, most folks are coming to me like, hey, I got some Pandas code. I want to dust it off, see what the level of innovation is and what can I do with it. So we've really expanded the level of higher level stuff. Pandas, for example. We take a lot of the Pandas functionality and accelerate it through Rapids. And it's really been an innovation of ease of use, essentially. The other area is, and this is more related to the engineering problem I deal with. I work in the automotive space, but that automotive space could be multiple dimensions. Could be automotive innovation related to autonomous vehicles, AI, AV, driver-assisted technology. Also, it's over in manufacturing, right? And so one of the things we run into here was, I went to a plant before COVID, and we were looking at a metal stamping problem, right? We stamp a given number of panels per hour, about every 5 or 7 seconds, one comes off the press, and we try to determine if it's a good panel or bad panel. Good stamp, bad stamp. Did it have all the hole punches, the dimensions, whatever, or accordingly and stuff like that. The interesting thing at the plant, they had no real data. They basically had somebody says, kind of like Bugs Bunny with the bomb, dud, dud, dud. I mean, they told me they had no bad panels. I'm like, wait a second here. You have no bad panels. So you want me to come in with innovation and a tool to look for bad panels, but now you claim you have none. What issue do you want me to solve, right? I mean, you guys, let's fess up. Why are you inviting me here if it's already been solved if you never have a bad panel, right? And they said, well, we don't really know if we have a bad panel. I'm like, oh, really? It's like, well, how do we look at this? How do we solve this, right? It's like, well, we know how much the car weighs when it's done, and we know how much the steel is when it comes in, and we know how much the scrap bin is, and we know how much the scrap bin is. Like, wait a second here, guys. So you can't tell me how many bad panels per hour or month you construct? No. So we started doing a bunch of data analysis and stuff like that, and we started realizing, it wasn't 10%. I mean, it was like that 1 or 2%, right? And even in some case, most of the time, even lower than that. But those panels were important because when you start putting them together in a cab or an A pillar, the A pillar or the B pillar, gets off or doesn't have the right holes, and some of those are hardened in certain ways that you can't even drill with a normal drill bit, right? It really matters, right? Because you have to use things like water drilling, on a basically bare metal, which causes corrosion problems, right? And stuff like that. So in this case, what we're really doing is Some of our new time series tools looks at data historically, right? But also allows you to rank order what's last in the hopper, because that's really what's important. Sort of that problem I just described, right? Historically, we never had a problem, right? Non-problem, we're here to solve a non-problem. Okay, that's a different one. And these new series of tools really allow us to look at the incoming data, right? The online data, the influx data, infrastructure to vehicle, vehicle to infrastructure type data. Do I have a deterministic problem, from a collision in the road system to manufacturing defect with a throttle position sensor, right? Things like that. And historically, I could look and say, well, we've never had a problem with a throttle position sensor. Well, that's irrelevant if I'm having one this month, right, of multiple vehicles. So that was one of the nice things about the CUDA frame. We have a whole bunch of tools to allow us sort of quickly rank order that data. Not that Pandas or numpy doesn't do it, but it does it really efficiently to allow us to pull and highlight those data attributes to the highest level. Other thing is we tend to support everything, PyTorch, TensorFlow, and stuff of that nature from the machine learning AI side. CUDA is NVIDIA's parallel graphics language. That's how we accelerate. But I think I've told Jared this over here a number of times, like, I came to NVIDIA, I was programming CUDA probably 5 times a month. I'd be lucky to say if I used it 5 times last year, So what we've tried to do is we try to basically isolate the end user consumer from having to know a parallel graphics language. We sort of give it to you for free, right? And we give it to you for free through all these libraries and all this software innovation. And pretty much we're pretty platform agnostic, right? And OS, right? If you're on x86 box, Intel, AMD, we also support ARM. ARM for things like, inside cars, inside your doorbell, inside your smoke detector, things of that nature. Your routers, we tend to be able to support all those devices. We also have this construct of our NGC. NGC is the NVIDIA Graphics Cloud. It's basically where we put containers that have been optimized by us to allow you to quick start, right? And I came out of the engineering space, right? So I will tell you, it's like, first I got to figure out what tools to have, then I go buy those tools, then I figure out how to use those tools, and now I can finally do something with it, right? The whole idea behind NGC is I just give you the tool and allow you to run tomorrow, right? And so it's already pre-packaged, ready to roll, and you can use it, download it for free, just sign up for the account, and you're good to run. I assume this will be published somewhere, but if you want to, we have a whole bunch of content there. Obviously, quick search will get you there, but we have everything, right? This is a starter kit, right? This is 101 to 511, right? I mean, we have all the fidelity there for you, and we have all the tools and features around Rapids. Anyone here use NumPy? I got a few users, right? So NumPy, from a Pandas perspective, is like a 10x or a 50x accelerator, right? It's really what it does is it takes the data, instead of the list of data and the classes, and basically gives you optimized methods and expression of your data. It compacts it, right? So everything on the page you get to use and take advantage of, right? But what's CuPy, right? Why do we do CuPy? NumPy exists, right? NumPy works on GPUs as well as CPUs. It's indiscriminate, right? It doesn't care, right? But how can we take it to the next level, right? And if we do take it to the next level, how do we make it easy for you to take advantage of? So CuPy is simply a drop-in replacement of NumPy. And the reason we call it CuPy is it's CUDA. It understands CUDA and accelerates to our best capabilities the operations you're doing, right? And the unique part is it isn't just simple math. It's not like, hey, I'm doing a matrix multiply, just go do it, right? We actually use all the power of artificial intelligence to look at how big that matrix is. So we know if your matrix is small, large, super large, if your matrix was very horizontal, right? More columns and rows, stuff like that. We know going in through AI innovation how to solve that problem more efficiently. In other words, let me take the task on versus you go, oh, I can write a really good matrix optimization, multiply. True. I mean, I even try to do it, not that I'm that efficient compared to some folks who have done it before me, but I can write it, right? But that's the problem. I don't want you to, right? And so the nice thing about this is I do those same NumPy operations, but not only do them mathematically correct, I use artificial intelligence to determine how to do them optimally to reduce the time of execution. So really, kind of redundant slide, but we pretty much match, NumPy for NumPy. It's sort of that bulk level, find and switch kind of philosophy, and you can go forward. And like I said, I'm a coder, I'm an engineer under the hood. I mean, most people walk to the car, and I walked and pull the hood latch and open the hood, so that's my nature. So open the hood here, right? On the left, in red, is NumPy. The green is NVIDIA with CuPy, right? Very minimalistic changes, right? So the unique value of this isn't, I don't want to come to your shop in your house and say, here, you need to change an entire process. You need to port this. You need to do all this work, right? I just want you to see if GPUs can help you in your innovation and discovery cycle, right? And so if I can make that easier for you and more attractive for you, I can actually get hopefully some latitude to do that with you, right? So I mean, that's pretty, pretty, right? And this is like another simple one, right? I mean, I don't know how many times I went to like a particular customer and said, oh, let's look at your code and let's change like 42 things and let's run it again, and bang, I get like, I've seen as low as 10%. I will say it's not always the magic one, but in problems that scale out to sort of larger dimensional things, like sort of the large, extra large, super large problems, I started getting 100x, 50x, 250x one time performance boosts over NumPy, which is supposed to be really optimized well, right? One problem is CuPy doesn't understand multiple GPUs, right? It gives you the constructs to dispatch it to multiple GPUs, and like in NVIDIA's case, and Dell and HP and all the other folks that sell our gear, they offer boxes with 1, 2, 4, 8, 16 GPUs in it, right? So CuPy yet today can span out to use the entire incumbents of all your GPUs in the box yet, right? It's on a roadmap, it's in our future, we'll get there, but right now it's sort of, I dispatch the work to a GPU, I can dispatch the work to another GPU, but honestly, as the end user, I have to do that operation today. We're getting there, but it's not there yet. So yeah, I pre-read my slide, I guess. So single GPU, that's where we stand today, but it gives you an amazing amount of acceleration. I've had instances where, more importantly, with things like in-flight transaction processing, right? And I always get concerned when people's innovation are, I could write a quicker report. It's like, oh, that's fine. But like telling me the traffic was bad on 75 this morning, I'm leaving at 5 p.m., right? Irrelevant, right, for my needs, right? So the interesting thing about GPUs and putting GPUs in that workflow loop, it could give you essentially aspirational know-how, right? Just like we breathe, right? I can give it to you in real time, some of these attributes, right? How the data is flowing, what the data looks like, how to do, extract, transform, and even learning on it. So that's one of the values of CuPy, right? It takes that dimensional problem that might take, a few minutes to a few hours to solve and potentially running in a stream real time. An example of that would be inferencing. Inferencing is be able to look at things like a dealership, right? A dealership, I could see the cars coming in, the cars coming out during the day and during the evening, right? As an example, I can get an understanding of what the floor traffic is, right? So one of the things we could do is take advantage of it and say, okay, it's really useful that if Mr. Jones walks up to the counter, I know it's Mr. Jones, right? It makes them feel comfortable, right? And one of the concerns today is the philosophy of the dealerships are probably going to change dramatically over the next decade. The reason is with internal combustion engines and traditional transmissions, it actually generates a large amount of foot traffic. These things need to be repaired and fixed. With electric vehicles, what's going to be the rate of repair or the rate of recall, right? So what you traditionally might use the dealership for, with electric vehicle, you might use it only 10% tomorrow, right? That's 50% of the dealership's revenue, right? So how does a dealership of the future make money, right? If no one ever has to come in to get their vehicle repaired, oil change, muffler redone, whatever. Not too many mufflers going bad nowadays. We realize stainless steel works. But it really changes the dynamics, right? And so one of the things we can do is look at inferencing. We can look at inferencing and make sure the whole dealership experience is better, right? Both from the customer interaction, customer educational stuff. I mean, I don't know how many times I've jumped into a rental car and like, what idiot designed this thing? I can't turn the air conditioning on, right? Things like that, right? I mean, how do we help facilitate that? How do we make people more comfortable, faster, and so forth? And so one of the things, we have a whole series of things related to like dealership innovation and customer experience related to vehicles. A little more couple snow code snippets. One of the other things I want to make mention of is, although our GPUs have lots of memory and lots of available memory, it's not an unlimited resource, right? And one of the things you can do is you can fence it off and kind of control the ebb and flow of it. And so one of the nice things with, unlike numpy, which will basically just try to allocate all the memory and then some, CuPy allows us sort of play traffic cop. Anyone here ever use a recommender? Anyone knows what a recommender is? Anyone ever use Netflix and says, if you like this, you should like that? That's a recommender, right? That's a recommendation system, right? Obviously for Netflix is just to keep you in the seat longer, absorb the ads, but in other cases there's a whole bunch of decisions need to be made, right? I had a particular customer problem that we were managing an assembly line process, and our observation of determining the correctness of the assembly line process was 4 stations down, right? So it's like, oh, I don't install this correctly, but I don't know the 4 stations down it was installed correctly. And I asked him, like, why is that? He's like, well, it's probably because it's another component needs to be put on top. That's the problem, right? If it's not there, it's not installed properly, I got a problem. I don't put the radio in upside down, I can't put the dash on, right? Stuff like that. So I'm like, oh man, that's kind of disturbing, right? And so one of the things is they were starting looking is like, and that was interesting about the human performance with the curling thing, right? Is I think of assembly line workers as athletes, right? They're going to do a particular task, and how are they doing the task efficiently, right? And so how this ties a recommendation system is, what a recommendation system does, it takes huge amounts of data, right? You experience it with Amazon, right? I shop for tools. So when I go to Amazon, I see other tools I might like, right? And so one of the things it does is it has a couple huge sets of data, right? On this side, there's a tabular data, and there's a click-through data on the, it's called huge CTR. There is what my choices are, right? Do I ignore the ad, pass through it, read it, spend some time on it, stuff like that? These data sets can be tremendously large, right? They can be large in multiple terabytes, tens of terabytes in some cases, right? And so what I have to do is deal with the ramifications of, I need to make a determination just like Netflix does and just like Amazon does to say, you spent time invested in X, maybe you might like Y, right? We're starting to use these recommendation systems to actually understand human behavior. So like on the assembly line floor, one of the things is I could actually recommend, maybe I do different operations at different times. Maybe I can see a person say, I've watched the video, every person bobs versus weaves, right? Things like that. And so we can come back and say, here, human factors, human capability, dexterity, and stuff like that, right? We could recommend different movement, right? Or different placement, or maybe rotating the vehicle in a different orientation to make that operation easier, right? So recommendation systems have a tremendous impact to our future. In fact, we're going to see it more and more every day. I mean, when we're typing, Word recommends the next word, right? Puts, wow, reads my mind. No, it's using a recommendation system behind the scenes, right? And what we're going to start seeing is more and more influx of recommendations, right? Because that is critical for our acceptance, right? And what really that is artificial intelligence looking at how we make decisions and how we respond and work accordingly. So the big section here is like scoring, right? That's, I watched Top Gun because my wife had never saw the original Top Gun. It was just disturbing. I mean, I was in the military, but the other night, because in preparation of seeing Top Gun, right? So now Netflix now shows me all these new, testosterone-driven male movies of that nature, right? And so that's sort of scoring, right? But my kids are different choices, right? My grandkids are different choices. They're looking at, Disney things, right? Like that. So Netflix is really confused, right? Because like, oh, this guy has a very diverse lifestyle, right? So scoring is a big thing, right? So if you start thinking about the whole human population, right? And everything looking from what cars and what features are useful, right? Is how you determine that, right? And so scoring that table is huge, right? 300 million people in America, right? How many decisions do you make on Netflix any given time, right? Maybe 100, 150. You're looking at tens of terabytes of data in minutes, literally, with places like Netflix. So this is where you're going to see us here, and it's going to grow. It's going to be pervasive to the point like we're trying to think for you. but what I like is I kind of told my wife is for Christmas or birthday, the safe bet's always ask her explicitly what she wants, right? But that's a cop-out, right? It's like, I want A and B. What she really wants to know is, does he know me well after 30 years? I can discover this by my own, right? And so one of the things is you might see in the future is that sort of, I'm not going to tell you what I want, but I can give you your recommended personality of me, right? And so when Amazon, I don't get a wish list, I sort of give what I like, right? And I don't have to invest a large amount of time. Like in my case, 30 years, I still get it wrong. But so 2 areas there, NV-tabular and the click-through, huge click-through. Accelerated, guess what they both use? Rapids, CuPy, right? We're getting the acceleration there. Rapids is available in containers. You can look at NVIDIA Rapids, download it. It's already pre-built. We actually have examples, both everything from financial perspective to even an automotive case or two. We have support for CuPy. It's very available, open sourced. Hopefully I kind of whetted your interest in it and take a look at it. MERLIN's a recommendation system where we take these tremendous amounts of data and we try to go do something with it effectively. And so we'll start to see in the future a large series of applications being developed on it, right? And that was it. Thank you for your time. Any questions? Anyone?
So is MERLIN like recommendation engine, is it built like on deep learning? You don't have to go in detail, I'm just trying to understand it more out of curiosity.
Yeah, so what ends up happening is a basic recommendation system is you kind of think of it, they call it like a sort of parquet format, is there's a scoring algorithm and sort of a personality or wants and needs, right? And essentially what we're able to do is by you giving us one, we can inverse that matrix, right? And give you sort of what you like accordingly, right? And that initial training actually is linear algebra, right? What we do is like anything we see mathematically wise, we use artificial intelligence and machine learning to sort of elevate its purpose, right? So the simple one was sort of when we first started recommendation systems, it was like, sort of 2D, right? Nowadays, if you think of it, it's more like a 3 or 4th dimensional plot, right? We have things, so on a given weekend, if it's raining, you might have a different movie preference than on a sunny day, right? You might be watching sports events, right? I have no idea, right? So that actually gets mapped to a curvature, right? And so we kind of use the AI techniques to look at, you know, three-dimensional, fourth-dimensional surfacing. So, any other questions? Awesome. Well, I thank you all for the time and consideration. Hopefully, if you have folks yourself or back at the shop that are interested in some of this stuff, it whetted your appetite. And like I said, it's a pretty low cost if you already have the code, just to see what a GPU can do to enable it in terms of acceleration and maybe understanding a larger volume of data. So thank you all again.